Hello everyone, this is the third lecture of our course EEE 4851 Advanced Communication Techniques. In this lecture we are going to discuss about a technique of wireless communication that is heavily used in the recent generation of mobile communication system. This is orthogonal frequency division multiplexing or OFDM. Now for this lecture, I haven't followed any books in particular. Some of the resources were taken from this book and some other books and also some internet sources. But if you want to know more about this topic, orthogonal frequency division multiplexing, then you can follow this book, Digital Communications by Bernard Sklar. From this book, you can go through chapter 15 to get a better understanding of this topic. So without further ado, let us begin this lecture. Now, first of all, let us talk about some of the strategies we have for increasing throughput. Now, what is throughput? Throughput of a communication system is the actual amount of data we can transmit through our system, right? Previously, we had heard about another term which is channel capacity, the theoretical maximum data rate we can achieve for a channel, right? But in general, our system also has some limit, and based on that, the actual amount of data we can transmit through our system is the throughput of our system. Now, how to increase this throughput of our system? From our previous lecture, we know that this was the formula for Shannon's capacity, right? So C is here the channel capacity, the maximum data rate we can achieve theoretically with our channel, right? And B is the bandwidth of the system, and S divided by N is the signal to noise ratio. So it basically relates our channel capacity with bandwidth and also signal to noise ratio. Now, based on this formula, we can already have some idea about how to increase our throughput, right? There are basically two ways we can increase our throughput. First one is to increase the transmitter's power. That means the value of S. If I increase the value of S, obviously S divided by N or signal to noise ratio will increase, which will in turn increase our channel capacity. So as we increase the channel capacity, obviously our throughput will also increase. Now the next one is to increase our channel bandwidth. If we increase the bandwidth, obviously this is related to our channel capacity linearly. As we increase the bandwidth linearly, our channel capacity will increase. In turn, our throughput will also increase. In reality, what happens is that using these two techniques alone, we cannot achieve the theoretical maximum limit of our channel capacity, that is Shannon's capacity. This is because the available resources of our channel, that is called the communications resource or CR, we cannot actually utilize these resources totally, like bandwidth or power. These kind of things are not properly utilized in traditional communication systems. As a result, we cannot achieve that theoretical maximum limit of our channel capacity. Now here, communication resource or CR means the time, bandwidth and power available for our communication in a particular system, right? So if we can utilize properly these resources, then obviously we can achieve a higher data rate, higher throughput. So as a result, we can say that there is a third method for increasing throughput of our system, that is allocating the communication resources efficiently and intelligently so that we can utilize all of the communications resource available for our system. Now, there are some techniques available for achieving this efficiency in our communication resource utilization. We are going to talk about two of them, multiplexing and multiple access, in this lecture. So here, using these two techniques, we can efficiently utilize the CR among our users. Now, what is multiplexing and multiple access? Now, these two terms, multiplexing and multiple access, both refer to the same thing, which is sharing of a CR. We want to share our communication resource among our users, that is multiplexing or multiple access. But there is a subtle difference between these two techniques, how they achieve this sharing of SCR. Now in multiplexing techniques, we have obviously multiple users which will have the allocation of our resources, but here you see we have 3 users as an example at the transmitter side, and we have a multiplexer. This multiplexer actually combines all of the signals before transmission. So before transmission we have this multiplexer so that all the signals can be combined together, and after that it is transmitted through our channel, and when it is received at the receiver, there is a demultiplexer which separates these signals so that it can be received by our intended receiver. So that is the idea of multiplexing. Now what happens in multiple access? In multiple access we are doing the same thing. We are sharing our resources among different users. Like here we have 3 users, TX1 up to TX3, but here we don't have any kind of multiplexer. That means these 3 signals go directly to our channel, and there obviously they will interfere somehow because of our nature of the channel, but at the receiver side we will have some intelligent techniques so that we can separate these signals so that the receivers can receive their desired signals, right? So that is the difference between multiplexing and multiple access. In multiplexing, we have a dedicated multiplexer to combine the signals before transmission. But in multiple access, the signals directly go to our wireless channel. There obviously they will get mixed or interfere, but we have techniques to separate them at the receiver. Now in this lecture basically we are going to talk about orthogonal frequency division multiplexing, which is a multiplexing technique, right? So before that we have to talk about the traditional type of multiplexing techniques. One of them is FDM, another one is TDM. So first of all, let's talk about frequency division multiplexing. So as we said before, in multiplexing or multiple access techniques, what we basically do, we just share the resources among the users, right? In frequency division multiplexing, that happens in frequency domain, right? So if you look at this figure here, so we have 3 users and then the signals get multiplexed, right? But after multiplexing, basically we have a separate frequency band for each of the users, right? So if I look at the channel, in the channel after transmission, each of these users signal takes a separate band of our channel, but in time domain every user get access of the whole time. So they are separated in frequency but not in time. And obviously at the receiver we will have a demultiplexer which will separate the signals based on some algorithm, and finally our receivers will receive the intended signals. So that is FDM. Now if we look at time division multiplexing, what happens, basically the same thing. We are sharing the resources among the users, but it happens in time domain. That means if you look at this figure, we have the same 3 users transmitting the signal, and we have a multiplexer to combine these signals. But after transmission, if you look at the spectrum, you will see that the sharing of resources is happening in time domain. That means the first user is getting this time duration, which is called time slot actually. So user 1, then user 2, user 3, again the 4th slot will be taken by user 1. So in this way each user is getting some time slot to transmit their signal, and finally at the receiver side we have a demultiplexer to demux the signal or separate the signals so that our receivers can receive the intended signals. So that is the basic difference between frequency division multiplexing and time division multiplexing. But in reality both of these things are used together. Like in the first generation of wireless communication systems in 1980s, we only used frequency division multiplexing, but when we came to 2G standards in 1990s, what happened is we used time division multiplexing also with frequency division multiplexing. So we were sharing the resources in frequency domain as well as time domain also. Now these are the basic types of multiplexing as we have discussed right now, but after third generations or at the beginning of our fourth generation standard of mobile communication systems, we had a new type of multiplexing technique, which is orthogonal frequency division multiplexing. Now currently for the recent generations of mobile communication systems like 4G and 5G, this is a basic building blocks, like many of the current modulation schemes like 802.11 WLAN, 802.16 WiMAX, and current 4G standard LTE, there it is heavily used, and it can support data rates more than 100 megabytes per second. So it's a very promising technique used in our current generation of mobile cellular standards. Now if we want to define OFDM in short, it can be done in this way. So OFDM is basically a special case of multi-carrier transmissions where we have a high data rate data stream, let's say, and we partition or divide that into some smaller low data rate signals. Okay, so from high data rate signal to multiple low data rate signals, and for modulating them we have low data rate subcarriers, multiple low data rate subcarriers to modulate them. So this is basically the idea of OFDM, and obviously as there is something called orthogonal in our name, all these subcarriers should be orthogonal to each other in OFDM. Now I know most of the things discussed here are not very clear to us right now, but as we go on further, obviously all of the things will be discussed and clarified. Now there are two key concepts to understand how OFDM really works. One of them is multi-carrier modulation or MCM, and another one is orthogonality. So first of all we will discuss about multi-carrier modulation, then we will start with orthogonality. Before we do that, let us understand why we are using OFDM. What are the benefits like? So first of all, let us define the problem. What are the problems we have right now and how OFDM actually tries to solve them. We have already talked about inter-symbol interference in our previous lecture. So let us consider a single carrier BPSK communication where we have a data rate or a bit rate of 10 megabit per second. So we can just simply say as this is a BPSK communication, in BPSK communication symbol rate is exactly equal to bit rate, because we have two symbols for BPSK, right? And also for bit also we have two states. That's why symbol rate is equal to bit rate for BPSK. We already discussed this in our previous lectures. So from that notion we can just simply say symbol rate of the system is 10 multiplied by 10 to the power 6 symbol per second, because our bit rate is 10 megabit per second, right? And if symbol rate is this one, then we can just simply find out the symbol duration as 1 divided by symbol rate, which comes as 0.1 microsecond. So symbol duration for this system is 0.1 microsecond. Now what is the traditional or typical delay spread of wireless channel? From previous lecture we already know that typical delay spread of wireless channel should be around 1 to 3 microsecond. So if I compare this value with this value, you see symbol duration is much less compared to our delay spread. So that is what is happening here. So we have a very small symbol duration compared to our delay spread, and what happens because of that? We have inter-symbol interference, as we had earlier discussed in our previous lecture. So this will happen, we will have a problem of ISI. If I want to see that graphically, you see we have this signal, okay? So we want to transmit this signal, these are particular symbols, and TS is the symbol duration, right? And for the system we have a delay spread like this, which is much larger than TS or symbol duration. As a result we will have severe inter-symbol interference. So that is what written here. Our requirement is high data rate. We want a high data rate and for that we need higher bandwidth. As we know from Shannon's capacity theorem, bandwidth is directly proportional to our channel capacity. That means if we want higher data rate or higher throughput, we need higher bandwidth. Now for that, as our data rate increases, our symbol duration will decrease. From the previous slide, we have seen that for increase in data rate, we have smaller symbol duration, right? And that will lead to inter-symbol interference, right? So first, let's discuss how multi-carrier modulation works in OFDM. So let us say we have a signal x of t, right? We want to transmit, and we have a traditional single carrier BPSK combination. First of all, let us just say we are trying to transmit this data x of t using traditional methods like single carrier BPSK communication. So obviously what will happen, we have the signal x of t, we will use a single carrier which is centered at frequency fc, so cos 2 pi fct will modulate our x of t, and finally that modulated signal will be transmitted to our channel. Now let us assume here the signal we are transmitting here that has a symbol rate of r, right? And obviously because of that we will have a symbol duration of 1 divided by r, just inverse of symbol rate. And also assume that after modulation our x of t in frequency domain occupies a bandwidth of b. So here this is graphically shown like this. So our signal has a bandwidth of b and centered at a frequency of fc. Let us also assume that the symbol rate we are taking here r, it is very high, so obviously the inverse of that, the symbol duration will be very low. So symbol duration 1 divided by r is very low, which is even lower compared to our delay spread. And we already know if our symbol duration is lower, much lower than our delay spread, what will happen? It will cause a severe inter-symbol interference at the receiver, right? So this is the problem we want to somehow minimize or mitigate. For that, let us take another approach. Instead of just using a single carrier, let us use multiple carriers. First of all, let us divide our bandwidth b into n subcarriers like this. So we have 1, 2, 3 up to n subcarriers instead of just one carrier of bandwidth b. So each of these subcarriers will have a bandwidth of b by n, and also if you look at this, each of these subcarriers have a center frequency of f1, f2, f3 up to fn. So this is what we are doing. We, instead of just using one carrier, we will use multiple carriers, actually n subcarriers instead of just one carrier, and our n carriers will take or occupy the same amount of bandwidth, that is b. So this is why each of them will have a bandwidth of b by n. So in total together they will occupy a bandwidth of b. So that is what is written here. So instead of just a single carrier cos 2 pi fct, we have now n carriers to transmit the same data x of t. So how to do that? Basically, as we have n subcarriers, we will also divide our signal x of t into n substreams. So starting from x1, x2, x3 up to xn, we will divide our main signal x of t into n portions or n substreams, which is done using a serial to parallel converter, right? So we are trying to achieve some kind of parallelism here. And the next thing which is very important is that previously our x of t had a symbol rate of r. Now our substream, each of these substreams x1, x2, x3, each of them will have a much slower symbol rate, which is r divided by n. So n times less compared to the previous situation of x of t. This is very important to understand. Just keep it in mind. Then what happens? Finally, we have n subcarriers and n different substreams. We will use these n subcarriers to modulate our n different substreams. That is done here. So the resultant modulated signals can be written like this: y1, y2, y3 up to y of n. In this table we can see that for example, if we have substream x1 of t, then the subcarrier is cos 2 pi f1t, and the modulated substream, which is called y1 of t, is x1t cos 2 pi f1t. So in this way all these modulated substreams will be generated, right? Now after these multicarrier modulations, obviously using a multiplexer, our n modulated signals, that is y1, y2, y3 up to y of n, these will be added together, then transmitted through our wireless channel, right? So now if I want to give a formula or expression for our multicarrier modulated signal, the combined signal that we are going to transmit through our wireless channel, that can be given as this. We are calling our signal as y of t, the modulated combined signal, and that is the combination of y1, y2, y3 up to y of n. Now if I just put the values of each of these modulated signals, then we will get a expression like this. We can further simplify it like this. So the final expression is y of t, which is the multicarrier modulated signal, combined signal, summation of I is equal to 1 up to n, and we have x of it, the actual substreams, and then the subcarriers cos 2 pi fi t. So this is our expression of the final transmitted signal. Now if I want to graphically represent what is happening at the modulator, basically we have a signal x of t which we want to transmit. We have a serial to parallel converter which will divide our x of t into n different substreams, starting from x1, x2, x3 up to x of n, and for each of them we will have a different subcarriers. But one thing to note here, each of these substream will have a much lower data rate, which is r divided by n. So previously here for x of t we had a data rate of r, right? But each of them, x1 we will have a data rate of r by n, x2 we will have a data rate of r by n, x3 we will have the same. So like this, right? Here also. And these n substreams will be modulated by n different subcarriers centered at frequency f1, f2, f3 up to f of n, right? Now that is our modulated signals, right? Or modulated substreams y1, y2, y3, yn, and these signals will be added together using a multiplexer, and finally the resultant signal will be transmitted through our wireless channel. Now finally let us discuss how multicarrier modulation actually minimizes intersymbol interference. So here in this figure you see the first row basically graphically represents our single carrier modulation. So here the length of x of t is assumed to be n symbols. So the total length of our x of t is n symbols, starting from 1, 2, 3 up to n symbols we have x of t. And we had earlier said that the data rate of our x of t should be r, right? R beats per second. So obviously our symbol duration, the duration of each symbol is 1 divided by r, 1 by r. So that is what is graphically represented here. Now if you look at this one, the first one, you see we have n symbols. After transmission we have only single carrier to transmit this whole signal. That's why a single bandwidth of b is drawn here, right? So this is the time domain representation, this is the frequency domain representation of our signal after modulation, after transmission. Now let us take the same signal x of t and try to transmit that using multi-carrier modulation, which is drawn here, right? So here first of all we said that instead of just one signal x of t, we will have n substream. So after dividing x of t, we will get n different substreams, x1, x2, x3, x of n, right? Also, another thing we said earlier, that each of these substream will have a much slower data rate, right? So that means if I want to say again, like for x of t we had data rate of r, and for x of I of t, that means x1 x2, these substreams have a data rate of r divided by n, which is n times smaller than our x of t, or the data rate of x of t. So what will happen in the symbol duration? Symbol duration will get n times higher, right? So that is what happening here. Basically for x of t we have symbol duration 1 by r, and for the transmission of x1 x2 we have n times, which is n by r as symbol duration. So compared to this, if you look at the symbol, this is basically x1 of t, which is expanded like this in time domain. So symbol duration is n divided by r. Same goes for x of t. So this symbol is expanded here like this. So in this way we have a much higher symbol duration, and for each of these substreams we have a dedicated subcarrier. So first one will be modulated by subcarrier centered at frequency f1. Second one will be modulated by this one. So in this way all of these substreams will be modulated by a dedicated subcarrier, and at the end we will have all these subcarriers spaced apart here like this, right? So like this, all of these subcarriers will be staying here in frequency domain, and obviously we will have some techniques at the demodulator or at the receiver side, so that we can extract all of these signals separately, right? Now what we can say here, what is the most important aspect of this diagram is that you see we have achieved some kind of parallelism here. So we are sending the same signal x of t, but we have divided that signal into n portions, x1, x2, x3, x of n, and these signals are transmitted parallelly. But as each of the signals have a much higher symbol duration, we are taking the same amount of time. So what is the benefit here? What we are getting out of this one? We are basically minimizing the effect of intersymbol interference, because you see we said when our delay spread TD is much higher than our symbol duration, then basically our intersymbol interference happens. So here the symbol durations were very small, right? That's why compared to delay spread they were small, intersymbol interference were happening. Now as our symbol duration got increased, compared to our delay spread it will become very high. Let's say for example we take delay spread like this. So this is the duration of delay spread. So previously duration of each symbol was very comparable to our delay spread. That's why previously in single carrier modulation we could have problems like intersymbol interference, but now our symbol duration is much higher compared to the delay spread, right? That's why now there will be intersymbol interference, but it is minimized because of this multi-carrier modulation. So that is what basically the advantage of multi-carrier modulation. We are minimizing intersymbol interference. So evidently a multi-carrier modulation technique increases symbol duration by a factor of n, as we had seen in the previous slide, and as a result delay spread becomes very negligible compared to our symbol duration, and the effect of intersymbol interference is now minimized. That is what we are getting out of our multi-carrier modulation. So now if we want to define multi-carrier modulation, basically instead of using just one carrier, we have multiple carriers. So we will divide our data, the data we want to transmit, into different multiple smaller data streams, and we will use multiple subcarriers to transmit them. That is the basic idea of multi-carrier modulation. But one very important thing here, these smaller substreams will have a very low data rate compared to the main signal. So after division, each of these signals will have a much lower data rate, because it will help us to minimize the effect of intersymbol interference. However, in OFDM, after this multi-carrier modulation, we have to do another step of modulation to elevate our signal to even higher frequency. This is done because, remember, we had two different reasons for modulation. One of them was for separating the signals of different users in frequency domain, and another one was to reduce the size of the antenna, because we know we use antennas for transmission of our signal, and the size of this antenna depends on the wavelength of our signal. So as the frequency is higher, wavelength will be smaller, and as a result our antenna size will be lower, right? So as we want our antenna size to be smaller, that's why even after this multi-carrier modulation, we have to again do modulation to elevate our signal to even higher frequency, right? For example, let's say IEEE 802.11a LAN standard, there the OFDM scheme has 52 subcarriers, and these subcarriers are spaced apart from each other with a spacing of 0.3125 megahertz. But after this modulation, this multi-carrier modulation, basically we have to again translate the signal to even higher frequency, that is 5 gigahertz range for transmission, right? So that is the whole idea about multi-carrier modulation. Now we are going to discuss about orthogonality. This is the second concept we need to understand OFDM. Now, first of all, let us understand what are orthogonal signals. For example, let us take two signals, S1 of t and S2 of t. They are said to be orthogonal for an interval of 0 to t if multiplication between these two signals, S1t multiplied by S2 of t, if integrated over a duration of 0 up to t, and if that results to 0, then we can say these two signals, S1 of t and S2 of t, are orthogonal to each other for this duration, that is interval of 0 up to t, right? So now this process, basically the multiplication of these two signals then integrated over a duration, this process is basically called inner product. So we have taken inner product of S1 with S2 for a duration of 0 up to t, right? Now we can go into further complicated mathematical detail, but I think a better approach would be to understand how orthogonality works with a graphical example. For example, we are taking S1 of t as cos t and S2 of t as sin of t, right? From this equation, we are going to take S1 of t as cos t and S2 of t as sin of t. And let's take the interval as 0 up to 2 pi. Then our expression will become like this, right? Now we are going to graphically see how this thing can be achieved, this orthogonality, right? So this is our expression, and if we look at the graphical representation, the green waveform here, this is the waveform of cos t, the blue one is sin t, and we have drawn it for a duration of 0 up to 2 pi. Now first of all, we have to take the multiplication or product of these two signals, cos t and sin t, for this duration, right? So that is what done here. If you look at this one, we have taken the product of these two signal, that is the waveform here, right? Now for this integration we have to calculate the area under this curve, right? First of all, we have multiplied, then drawn these signals, which is cos t multiplied by sin t. Now we have to calculate the area under this curve for the duration of 0 up to 2 pi. And simply you can understand that the area here is 0 because the positive areas here will be cancelled out by this negative area, right? So total area is definitely 0. So this expression basically becomes or comes as 0. So we can say cos t and sin t, these two are orthogonal to each other for the interval of 0 up to 2 pi. So graphically we have understood what is orthogonality. Now what if there are more than two signals? Can we define orthogonality then? To do that, let us assume that we have n mutually orthogonal signals starting from S1, S2, S3 up to Sn. We have n signals which are orthogonal to each other, and they are orthogonal for an interval of 0 to t. Now if I want to define orthogonality in this case, let us just take two signals from this combination of n signals, Si of t and Sk of t. Then they should hold the following properties, which is this one. If I take the inner product of Si and Sk for the interval of 0 up to t, then what will happen? It should come out as 0 whenever I is not equal to k, and a constant non-zero value Ci whenever I is equal to k. That means each of the signal whenever taken as inner product like S1 with S2 or S1 with S3, after inner product for an interval of 0 up to t, it should return the result of 0. But whenever I take the inner product of itself, like say S1 with S1 or S2 with S2, that will result in a non-zero value, a constant value, that is Ci. That is what we are trying to say here, right? Now what is the importance of this orthogonality? To be more specific, what is the importance of orthogonality in our communication system? Can we describe that? For doing that, let us take a function f of t, which is a linear combination of n mutually orthogonal signals like described here. So f of t can be described like this. So we have n mutually orthogonal signals S1, S2, Si up to S of n, and we are taking the linear combination of them. So you can take this A1, A2, AI, these are just basically amplitude of our signals. So just a constant. That is what written here. So this A1 up to AN, these are just the amplitude of the corresponding signals, can be considered as constant, no problem. Now what will happen if we take the product between our signal f of t with one of the signals Si of t inside, right? So if I look at the expression again, you see here we have f of t, which is the whole signal, and it is the linear combination of n different orthogonal signals, and we are taking inner product of f of t with Si of t. What will happen then? That is what we want to understand. So let us take the inner product here, f of t, Si of t. If I do that, first of all, let us just put the value of f of t, which is this one, right? Then multiply with Si of t like this. So we have n different integrations, right? So first one is the integration of S1 of t with Si of t, or simply you can just say it is kind of the inner product of S1 of t with Si of t. Second one is inner product of S2 of t, Si of t. A1, A2, these are just constant. We can put it outside if we want, no problem. But here as all of these signals starting from S1, S2 up to S of n, all of them are orthogonal to each other. Because of that, we can say that all of these integrations or inner products are resulting a zero value, right? Because we know if two orthogonal signals, we take inner product of them, then it will result in zero. But here we are taking the inner product of the same signal itself. So Si with Si, that will not result in a zero value. It will have a non-zero constant value. As we had discussed earlier, the constant non-zero value of Ci, right? So for all other integrations or all other inner products, we are getting a zero value, just not here. So we can just write 0 for all of these, and here we have a non-zero constant value which we will calculate right now. Here Ai is a constant, so we can just put it outside. That is done here. And if you take the inner product of Si with itself, that will come out as a constant non-zero value. That is Ci. We are just assuming. So total value comes out as AiCi. From this example, what can we derive? We can derive that we have extracted the information of Si of t. What is the information? This amplitude Ai. Previously, we had seen that our f of t is just the linear combination of n different signals. Each of them have a different amplitude, which is a1, a2, a3 up to an. These are the information lying inside of each signals. So we are just taking inner product with one of the signals S of I, and that is returning us the value of Ai, the amplitude of Si of t. So this is the powerful implications of orthogonality. So just by taking the inner product of Si of t, we are extracting the information of it. So this is what will be used in OFDM, also in some other aspects of communication systems. Like for example, let's say in our first lecture we had quadrature modulator, right? There we used two different carriers, cos 2 pi fct, another one is sin 2 pi fct. They are actually orthogonal to each other, as we had graphically seen in the previous slides, right? So because of that orthogonality, we can extract the signals or the informations lying in each of these carriers. So that's why we had two different carriers which are orthogonal to each other, and as a result we could extract the information, the in-phase component and quadrature components easily, right? So that is the property of orthogonality. Now let us understand how this orthogonality property is being utilized in OFDM. To understand that, let us take the same kind of signal x of t, which is a BPSK data stream. It is shown here like this, right? But before understanding x of t, let us understand what kind of representation we are using. We are using bipolar symbol representation. That means for representing binary 1, we are going to use amplitude of 1 here, like this. For representing binary 0, we are going to use an amplitude of -1. Now then, let us also assume for this x of t, this x of t has n symbols, right? So as you can see, starting from this symbol up to now, we have n different symbols for x of t, and from the idea of OFDM, we know our x of t should be divided into n different smaller substreams, data streams, right? These are x1, x2, x3 up to x of n. Now, as our x of t has n symbols, each of these substream will have one symbol, right? Like here, x1 of t has one symbol. This one, x2 of t, has this symbol like this. So each of these substreams will consist of only one symbol. Now from our previous discussion or previous derivation, we can say that after multi-carrier modulations, our modulated signal y of t can be written like this, summation of all the modulated signals. So this is further expanded like this. Here you see each of them is basically a multiplication of our substream with our subcarrier, right? Now we want to do something here, simplify something. That is, you see, as we have assumed that our x of t has n symbols and each of the substreams has only one symbol. For this one, for example, if I say x1 of t, for the whole duration of x1 of t, the value is constant. It is not changing with respect to time. That means we can just simply say xi of t can be said as xi only without this t portion, because for that whole duration these substreams are not changing. It is constant and not changing with respect to time. So this assumption will be used here. So here each of these cases we can just omit the t portion, right? So that is done here. So yt can be rewritten like this, where x1, x2, x3, x of n is without any time dependent portion. Now here, if you look at this expression, it can be compared with our previous signal f of t, which we used to show the importance of our orthogonality, right? So f of t was like this: a1 s1 of t plus a2 s2 of t plus a3 s3 of t up to an sn of t, right? So here a1, a2, a3, these were just amplitude constants. The same thing here, x1, x2, x3, these are just constant, and these are the signals, right? Like s1, s2, these are the signals. These carriers are the signals. Now, if we can make these carriers, these subcarriers, orthogonal to each other, then we can take the same assumptions we taken for f of t, right? So that means basically if these subcarriers are orthogonal to each other, that means if I take f1, f2, f3 such that the signals are orthogonal to each other, then just by taking inner product of each of this component, we can extract the amplitude x1, x3 of t, x2 of t. This can be done. Let's say, for example, we want to extract the value of x2. What we do? We just take the inner product of y of t with this carrier cos 2 pi f2t. If I can take the inner product of these two for the duration of 0 to t, then we are going to extract the value x2. As we discussed earlier, for orthogonality, this is what we can do. So that's why in OFDM, these subcarriers, n subcarriers, are taken such that f1, f2, f3 up to fn, these are all orthogonal to each other. And because of this orthogonality, we have two significant advantages in OFDM. One of them is these subcarriers, these n subcarriers can overlap with each other in frequency domain, which we will see very soon. So because of that, as the subcarriers can overlap with each other, still we can extract the signals. Because of orthogonality, we have increased bandwidth efficiency. And another one is because we have some mathematical relationship between these subcarriers, the demodulation process is much easier compared to our traditional process of using a bandpass filter. So we can just use some kind of integrator or modulator, you can say, that will help us to extract the signals in the demodulator portion. So we will see that very soon. So let us try to see those things, these two advantages, how we are achieving that, how it looks like. But before that, we need to first inspect how OFDM frequency spectrum actually looks like. So for that, we are taking the same assumption that we are sending a BPSK signal, and for that, after modulation, how it looks like actually in frequency domain. So we are basically modulating a symbol SI of t with a carrier of frequency FC. So this is the symbol we want to transmit, XI of t. It looks like this in frequency domain, which is a sinc function, right? So if you take a Fourier transform of square pulse like this, that will result in a sinc function like this. Sinc function basically should be something like this. So sine of f divided by f. Okay, so this is simply a sinusoidal signal, but the amplitude is decreasing as the frequency is progressing like this, right? Because we have a factor of f at the denominator. Because of that, as the f is increasing, this value is decreasing, right? So as a result, we are getting a sinc function. Now that is not the thing we understand here. We have to understand how a modulation changes this frequency domain representation. So if I take this symbol xi of t and modulate that using this carrier signal cos 2 pi fct, which is centered at center frequency of fc, then in frequency domain we will have the same type of signal. The shape will be very similar. The only difference is it will shift, the center of this signal will shift to fc frequency, right? So if we understand this property, then we can look at the next slide where we have n different modulated signals, right? So these are the n subcarriers with a carrier frequency of f1, f2, f3. So we already know that we need n subcarriers for this kind of modulation in OFDM. But for OFDM, we also have to have some kind of orthogonality property among them. So that is what is done here. So if I look at all the signals combined, all the subcarriers combined, that can be shown like this, right? So we have n subcarriers spaced in such a way so that they can hold the orthogonality property. So graphically, if you look at that here, for each of them, the maximum value of each subcarrier occur at a point at which the value of other subcarriers are 0. So basically, if you look at this subcarrier with center frequency f2, so here the maximum value is here, right? So maximum value is here, and here all the other subcarriers have 0 value, right? Here if you look at this one, so we have 0 value whenever f2 has the maximum value. Same can be said for f3 also. When f3 has the maximum value, all other subcarriers have 0 value. So because of this orthogonality property, even graphically we can say that to extract the signals or the information from one subcarrier is easy, because when we have the maximum value for one subcarriers, at that point all other subcarriers have the lowest amount of value or almost 0 value, right? So that is one advantages of using orthogonality in OFDM. Now because of this orthogonality, how OFDM signals are received or detected at the receiver, that can be shown using this graphical representation. So basically what we do, we just get the signal here from the wireless channel. Let's say we received the signal y of t, that can be multiplied with the corresponding subcarriers to get the corresponding substring. So we are multiplying the same signal y of t once with cos 2 pi f1t, once with cos 2 pi f2t, like this up to cos 2 pi fn of t, and each of these are extracting the corresponding substring like x1, x2, x3, like this. This is possible because all these subcarriers or all the signals we received have orthogonality property. Otherwise we couldn't do this kind of things. And as a result, we are getting n different substreams which we generated earlier at the modulator, and using a parallel to serial converter, we are just going to combine all of them and finally get our desired signal x of t. Now we can finally talk about cyclic prefix. So what is cyclic prefix? We know that in OFDM we basically try to minimize our intersymbol interference effect. But can we totally eliminate that? Obviously not. There will be some amount of delay spread always available, and because of that there will be some ISI. To completely eliminate the effect of intersymbol interference, we have cyclic prefix. So what do we do? Basically, if you look at the first one here, we are trying to send the symbols or transmit the symbols like symbol 1, symbol 2 and symbol 3, and there is no gap in between them. This is the symbol duration of each symbol, TS. Now for cyclic prefix, basically we put a guard interval between each symbol, so that the effect of intersymbol interference can be totally eliminated. Basically what we do is in that gap here, in this guard interval, we copy a portion at the end for each symbol. So for this symbol we have this portion at the end, we copy that and then put that in that gap or guard interval, and this portion here, this is called cyclic prefix. Now this is done just before transmission. So after multi-carrier modulation of OFDM, after that we put this gap or guard interval between each symbol and copy the end portion here at the front and then send each symbols. So this is the basic idea of cyclic prefix, and always we have to remember that the duration here, the duration of guard interval should be longer than our delay spread, because we want to totally eliminate the effect of our delay spread. As a result, we have to use a guard interval which is larger or longer than our delay spread. If I want to show you graphically what happens, basically because of our effect of delay spread, intersymbol interference happens like this. So for the symbol 2, some portion will come here like this. From symbol 1 also some portion like this will come at the receiver, and this portion basically will cause our intersymbol interference. So for each of the symbols, some portion comes at the beginning which is undesired, and also at the end also which is undesired, right? Graphically we can show it like this. So if I put a gap here, what happens? This undesired portion will be here, which we do not want, right? So it will not cause any kind of problem, and we cannot just keep it blank. When we transmit a signal, we cannot just keep a blank portion here. That's why we have to use this end portion for each symbol that is copied and put here in this guard interval. There is also some other benefits of this cyclic prefix in equalization, which is beyond the capacity of this lecture. But basically the idea of cyclic prefix is this. So then finally we can look at the overall workflow of OFDM. So this is the transmitter portion basically after modulation, and this is the receiver portion which does the demodulation process. So here you see, if you look at this one, x of t is the signal we want to transmit, and we had earlier seen that we have to use some kind of serial to parallel converter so that we can divide our signal x of t into n different substream, x1, x2, x3 up to x of n, and each of them will be modulated with a subcarrier, a dedicated subcarrier, that is f1, f2, f3, fn centered frequency subcarriers, right? And after modulation we have n different modulated substreams, y1, y2, y3 up to yn. It will go through a multiplexer, will be added, and finally we get the combined modulated multi-carrier signal which is y of t. And now, as we had seen, we have to use cyclic prefix. So after getting y of t, we add a cyclic prefix in front of that, and then finally we use the up converter. So what is up converter? We had said earlier that we have to again modulate our signal to a higher frequency for transmission because of the situation of antenna, right? So that is done using our up converter. So it is elevated to a even higher frequency, and then using our antenna we transmit the signal, right? Then this transmitted signal will be received by our receiver, and then it is again down converted to a lower frequency. Then we remove the cyclic prefix. After that we are getting the y of t we generated here, right? So this y of t will be going through n different modulators again. So these n subcarriers will again be multiplied with our y of t to extract n different substreams, x1, x2, x3 up to x of n. And these n substreams will be again added together or combined together using our parallel to serial converter, and finally we are getting the desired signal we want, x of t, at the receiver. So that is the overall diagram of OFDM, transmitter and receiver. Now if I want to compare traditional FDM, frequency division multiplexing, with OFDM, the first difference is the subcarrier spacing. In FDM system, basically these carriers or subcarriers has to have some kind of gap between them, guard interval, because these carriers doesn't have any mathematical relationships among them like orthogonality. As a result, we have to use conventional devices like bandpass filters to extract the signals. So some bandpass filter centered at frequency f1 will extract the signal here, right? So in this way we have to have much more bandwidth because of these guard intervals, right? Guard bands it's called. But for the case of OFDM, obviously we know that each of the subcarriers doesn't need any kind of guard bands. Further, we can even overlap the subcarriers because we have the property of orthogonality. As a result, even after overlapping each other, we can extract the signal easily. So because of this overlapping situation, you see always we have 50% overlap between the signals, right? As a result, we achieve a factor to bandwidth efficiency. We can send much more signal in the same bandwidth using OFDM compared to FDM. Now another difference is that the number of users. Traditional FDM or frequency division multiplexing is always intended for multiple users. So each of these carriers will be dedicated for a single users, and we transmit all of this signal together in frequency domain, right? But in OFDM, the whole thing, the whole subcarriers, these n subcarriers are dedicated for one user. So we had seen that for a single user we had a signal of x of t. We divided the signal into n portions, and for each of this portion we were using a single carrier like f1, f2, f3. So that is another difference between FDM and OFDM. The third difference is basically in detection method. We had already said earlier that in FDM, among the subcarriers there is no mathematical relationship, and as a result we have to use the traditional type of detection methods like using a bandpass filter to extract the signals. So these are called non-coherent types of detection process. In coherent type of detection, whatever frequency and phase we have used at the transmitter side at the modulation process, the same frequency and phase is used at the receiver side to extract the signals, like we had seen in OFDM, right? We used the same carriers, same subcarriers, and multiplied with our signal to extract the substreams, right? So that is coherent detection. So in OFDM we use coherent type of detection because we have orthogonal relationship between them, and in FDM we don't have any kind of relationship like that, so it will be difficult to use this kind of coherent type of detection. We use traditional filters, bandpass filters, to extract the signal. Now the last one, which is OFDMA, or orthogonal frequency division multiple access. So this is just the multiple user variant of OFDM. So far we have discussed about only OFDM, and in OFDM we have only one user. In reality, let's say in recent generations of mobile communication systems where OFDM is used, we have OFDM with TDM. Okay, so that is shown here. Like you see, we are sharing the resources in frequency domain and also in time domain. And we have 4 users, and this single time slot is dedicated for one user. So this is for one user, this is for another user, like this. But these small portions here you see, these are the subcarriers. So in total we have 12 subcarriers here dedicated for one user. For this time slot, user 1 will get all the subcarriers. For this time slot, whatever subcarriers we have available, all will be dedicated for user 2. So in this way, in OFDM, this sharing of resources happening. So for each time slot, we have only one user. And what happens in OFDM, as this is a multiple user variant, basically for each of the time slot here, we can dedicate subcarriers for different users depending on their uses. So you see here, for this time slot, we have 3 users using different subcarriers. For the yellow user, user 4, we have 3 subcarriers dedicated. For the blue one, we have 4 subcarriers. So in this way, depending on their condition of channel, depending on their uses, we basically dedicate some amount or some number of subcarriers for them. So this number of subcarriers dedicated for one user, so like let's say here 1 2 3 4 5, these 5 carriers are dedicated for user 1, the green user, right? These 5 subcarriers in together are called subchannel. Okay, and the advantage of using this kind of process compared to OFDM is that we can dynamically change the number of subcarriers used for each user. Obviously, all of the users will not have the same channel condition because their distance is different, their channel path is different, and also their requirement uses is not same. Some user is using more data, some user is not using that amount of data. So based on that, we can dedicate the number of subcarriers for them based on their situation. And another very important aspect is that you see, for this subchannel, these 5 subcarriers, I can change the modulation order based on the situation of channel. So let's say for this user here, he is very close to our transmitter, but for this user, the yellow user, he is not very close to our transmitter. As a result, we are going to use BPSK for these 3 subcarriers, and for these 5 subcarriers, as the user is very close to our transmitter, network condition is very good, that's why we can use a higher modulation order, like let's say QPSK or 16 QAM, like this. So in this way, we can dynamically change the modulation order and number of subcarriers based on the user situation. That is the basic advantage of OFDMA compared to OFDM. That's all for this lecture. Thank you.